Hi, in this video, I'll be going through what are known as Principal Ideal Domain, or in short, PIDs. So, in the last video, we have proven that every Euclidean domain is a Principal Ideal Domain because a Principal Ideal Domain is an integral domain in which every ideal is principal. And we already seen that Euclidean domains have this property where every ideal is principal. And so we abstract out that property and now we define a more general integral domain known as the principal ideal domain. And so some examples will of course be any Euclidean domain that we've already seen, such as the integers. And since the polynomial ring contains non-principal ideals such as the ideal generated by 2 and x, then it's not a PID. And we also see that the quadratic integer rings is not a PID. And so some propositions for us to prove PIDs is, now you have PIDs and you have integral domains at one level. So PIDs is over here and Euclidean domains are inside PIDs. We already know Euclidean domain, we can define the GCD and stuff using the norm. But what we want to say now is that in a principal ideal domain, we can also define a GCD. Even if you cannot do the Euclidean algorithm on it. And how we define it is by abstracting out the properties that we see are common in Euclidean domains, where we already know that D is the generator of the principal ideal generated by A and B in the Euclidean domain. Then we see, and we from that D we already denoted as the GCD. So now we can use that and say that is the GCD for A and B, and that D can be written as a R linear combination of A and B. So there are elements x and y such that D equals to AX plus BY. And then D will be unique up to associates. So it's a multiplication by unit. And really this is just the propositions that we see in our Euclidean domain side. And so we won't run it through. And since we already know that maximal ideals are always prime ideals, but the converse may not hold true, what we like to note that it is true in PIDs, and now we'll prove it. So every prime ideal in a PID is a maximal ideal. And the proof follows because if you're a prime ideal, but because you're in PID, you're generated by one element. And now we let I be any ideal containing this prime ideal. So we will show that it's maximal. So now you let P be an element of M. And so P equals to Rm for some R. Since P is prime ideal, this means that Rm must be an element of, and Rm is an element of this ideal. Either R or M must lie in P. If M lies in P, then P and M generate the same thing, which means that the prime ideal equals to I. On the other hand, if R is an element of P, then it can be written as PS. And so P equals to P times Sm, and this means that Sm equals to 1. And so M is a unit, which means that the ideal generated by it will be the whole of R. And so this proves that every prime ideal in a PID is a maximal ideal. Now we'll come to the concept of Noetherian rings, and this is a commutative ring that satisfy the following chain of condition of ideals, that you have a chain of inclusion for the ideals, so a chain of ideals, then there will exist a cutoff such that all of them are equal to each other. Or equivalently, you can just think the union of all of them is just IM. And now we'll prove that a principal ideal domain is Noetherian. So you just let it be a chain of ideals, then I equals to the union of this whole thing will be an ideal. And since R is PID, that means this I will be generated by some single element. So it must be that X is an element of IM for some M. And hence, I equals to IM. And this finishes the proof. So it's very short and simple. What's more complicated will be now showing that a commutative ring is Noetherian if and only if every ideal is finitely generated. So suppose I is an ideal, and then by the well-ordering principle, by fixing a well-ordering on the integers, on the ideals, I naught equals to the 0 ideal, and we can define inductively as the following. And so this gives us a way to say that IK will be a subset of IK plus 1. And IK is finitely generated. If R is Noetherian, then IK equals to IK plus 1 for some K, and thus I equals to IK is finitely generated. And we're done. Now suppose that every ideal is finally generated, and suppose C is a linearly ordered set, then with that we can see that I equals to the union of these I alphas, and we let G be the generators since it's finally generated. Then for each element there will be some I alpha such that Gi is the element of it. And so we just take the maximum one, and this means that G must be a subset of I alpha, which implies that I equals to I alpha. And so every chain has an element equal to its union, and in particular, this we can just take every chain again and show that R is Noetherian. Next, we say that an element is irreducible. Firstly, you must satisfy that it's non-zero and not a unit. Then we say that it's irreducible if whenever R equals to AB, then at least A or B must be a unit. And now we say that an element is prime if the ideal generated by it is prime. Or you can, in other words, say that whenever A divides AB, then either P divides A or P divides B. And your associate if two elements are equal to a unit times the other element. And so in the integral domain, a prime element is always irreducible. And you can prove that by saying that suppose P is some prime ideal and P equals to AB, then AB being an element of this ideal must be either P divides A or P divides B. This means that let A will be in the principal ideal generated by P. And so A equals to PR for some R. And this implies that A equals to P equals to PRB. And so RB must equals to 1, which means that B is a unit. And this shows that P is irreducible. But this is not true in general. that an irreducible element is necessarily prime, and you can consider the quadratic ring, integer ring, as the following, and see that the following does not break up as the way you wanted. And so we have another proposition that says that in a pre-ID, then any non-zero element that is prime is irreducible, and the converse holds true. So if and only if. And we already shown that prime implies irreducible, so now we must show that irreducible implies prime. And so if any ideal containing this ideal generated by P, then by hypothesis M equals to some principal ideal, and since P is an element of M, it means P equals to Rm, and P is irreducible, so by definition R or M is a unit. This means that either P equals to this ideal or P equals to 1. Thus the only ideals containing P are P or 1. So this means that P is maximal, and since maximal ideals are prime ideals, we are done. So this gives us another proof of why this quadratic integer ring cannot be PID, because we already showed that there are primes which are not irreducible in this ring. And lastly, what we like to take note now is what is known as a unique factorization domain. And that is really an integral domain which any non-zero element R, which is not a unit, has the following properties. It can be written as a finite product of irreducible PIs, where R equals to P1 to P can be multiplied to Pn, and the decomposition is unique up to associates. So if there is another decomposition, then they are equal in terms of number of terms here, and there are some factors such that Pi is an associate to Qi for all the i's. So a field is of course trivially a UFD, since every non-zero element is a unit. And as indicated above, we shall prove shortly that every PID is a UFD also. And so the UFD also has the property that every non-zero element is prime if and only if it's irreducible. And this follows because by proposition 10, primes are irreducible. It remains to prove that each irreducible element is a prime. So we let P be irreducible and assume that it divides AB. We must show that P divides either A or P divides B. To say P divides AB is to say that AB equals to PC for some C. And writing AB as a product of irreducibles, we see that this last equation, and from the uniqueness of the decomposition of the irreducibles of A and B, that the irreducible element P must be associated to one of the irreducibles in the factorization. And let's just assume that P is associated to the irreducibles in the factorization of A. This means that A can be a written product of UP times all the way to Pn, for U being a unit. But then P divides A, and since A equals to PD, with D being this, it completes the proof. And with that, we can also define a way to get a greatest common divisor in UFD. And that is the following proposition over here, which states that the GCD of A and B is just equals to the primes to the power of the minimum between the two elements A and B over there. So this is really very similar to the integers already, and we're just trying to abstract more and more properties out of it. So you can verify for yourself why this is the GCD, and I'll leave it to you, as it's very routine to just read through the arguments presented already in the book. What I shall now say is that every PID is a UFD, and while the book has a way of presenting it, I'll use another method over here. So we shall first claim that the element R is an irreducible factor. So if R is already irreducible, we are done. So suppose that it's equal to AB. Since neither A or B are units, then if A is irreducible, we are done. Otherwise, A can be written as AB, and we can have a chain of ideals. So we can keep dividing off. And then it will reach a point that because PIDs are Noetherian, then it will reach a point where it stops. And so it terminates at AN, and this is irreducible. So this finishes our claim that R must have an irreducible factor. And because of that, R is a product of these irreducible elements. And then you just check that now the factorization is unique up to associates, and this proves that every element can be written, every non-unit element can be written in some factorization, which satisfy the condition for the unique factorization domain. And so, from this video and the previous one, we have now seen examples where there's Euclidean domains, PIDs, UFDs, and integral domains. And the overall picture will be that the integers is a Euclidean domain, but it's not a field. So all fields are Euclidean domains, as we already proven. And we have also seen that there are rings that are PIDs but not Euclidean domains. So these are all proper subsets. The PID is greater than Euclidean domain. And then we see that the polynomial ring with integral coefficient is a UFD but not a PFD. And that this ring is now an integral domain but not a UFD. So it's really a structure as the following presented over here. So this is all for this video. I hope you have enjoyed it. Feel free to like, share, and subscribe, and I'll catch you in the next one. Bye.